So one of the favorite sections of the textbook, Chapter 8, internal flow, pipe flow. If you're a mechanical engineer, you're dealing with heat transfer, you have fluid flow inside of ducts or pipes, conduits of some sort. Often they're round. They're just pipes. They're tubes. It's very simple. So what do we do to start off this important chapter, internal flow? We start with section 8.1. What does that sound like? Hydrodynamic. Before you get into any thermal considerations, you have hydrodynamic considerations. It sounds like a review of fluid mechanics. So we'll talk about the flow, the mean velocity, developing region. It takes a while when you enter a pipe to become fully developed, and then whether or not it's turbulent, laminar flow, the Reynolds number, and then how do you calculate the pressure drop over a length of pipe? Well, you use the friction factor. Where do you get the friction factor? Some equation or even a chart, the Moody chart, the most famous chart, I would say, in the fluid mechanics class that you're exposed to, how to get that friction factor. Okay, so let's jump into it. So we have a pipe, and often it's important how you get the fluid into the pipe, and it's important as to what's happening. Let's say there's a big tank that's supplying it right here at the corners. And they could be well-rounded, they could be sharp, they could be protruding into the tank, and all that's important for the fluid flow. But let's say they're slightly bell-mouthed like this, so I don't have a big separation region like that. And the flow takes a while. Early on, the flow is flat and then has a sharp gradient. So the velocity profile is nearly flat in the core of the pipe, but there's a sharp gradient. But after a while, it develops and it becomes, especially if it's laminar flow, a nice quadratic velocity profile. What do you mean by quadratic? Well, measure as a function of R going out from the center of the pipe. R goes from the center of the pipe to the wall of the pipe. Let's call that cap R. And when it's fully developed, you'll have a quadratic. If it's laminar flow, it'll be quadratic. It'll be a nice shape. But it takes a while for it to become fully developed. Hydrodynamically, where the velocity profile, as you continue to go down the pipe, isn't changing anymore. It's not a function of x. So this would be a measurement of x, and the velocity profile doesn't change. Okay, so a couple questions. How can you tell if the pipe flow is going to be laminar or turbulent? Calculate the Reynolds number. What is the definition of the Reynolds number? Yeah, rho V d divided by mu, right? You can also work it out in terms of mass flow rate, but I'll just leave it at that. Most people have that memorized right here, rho v d over mu. And then what is the critical Reynolds number, where you say, if the Reynolds number is below that value, then I suspect it's going to be laminar flow in the pipe. Or if it's above this critical Reynolds number value, I suspect it's going to be turbulent flow in the pipe. So what is the critical Reynolds number? Around 2300. Again, it's just a number, it's rough numbers. Some people put 2100. Some people just round it off to 2000. Can you have it become turbulent at 1800? Well, yeah, if you have some perturbation in the system, if the wall of the pipe is shaking or moving, yeah. Often can you have it laminar longer, a higher Reynolds number? Yes, but it has to be very quiescent. I mean, just no vibrations in the system. But often in a mechanical plant and other things, you do have turbulent flow. It's more common to have turbulent flow in pipes than laminar flow. What is this entrance region? Let's call this the distance x to become fully developed, and because we're going to consider thermal considerations after hydrodynamic considerations, we'll first talk about hydrodynamically fully developed. So what is the equation for that to become fully developed hydrodynamic? Well, it depends if you're anticipating the flow to be laminar or if you're anticipating it to be turbulent. So if it's turbulent, it has a much simpler equation that I would just round this off and say it's approximately how many pipe diameters? Do you remember this one? How many pipe? Yep, 10. 10D. 10 pipe diameters. And if you work in fluid flow and pipe systems, you'll just see 10 diameters, 10 diameters, 10 diameters. It continues to come up. Often after a bend or a turn, you want to reestablish the flow to be fully developed, or where the velocity profile is not changing as you're going down the pipe anymore. And so they'll say, okay, if you want to put a flow meter into the system, that flow meter anticipates a certain velocity profile, hence it needs to be located 10 diameters down from the last disturbance, like a bend or an elbow. You'll see that a lot. So 10 diameters. Okay, well, if you do have laminar flow, it's 1/20th or 0.05. That's the same as 1/20th. Diameter times the Reynolds number. And you can play some games here. You can say, let me just write it like this. It's a little easier if it's 1/20th. Let's say the Reynolds number is 2,000. So just say, if the Reynolds number is 2,000, how many pipe diameters do I need to be away from the entrance before it's fully developed, if it's laminar flow? 2,000 divided by 20, what do you get? 100. So it could be that to be fully developed hydrodynamically, you need 100 diameters. That's a long distance. Let's say the Reynolds number is 200. How many pipe diameters would you need if it was laminar flow? 10? Let's say it's 20. I know this is kind of ridiculous, but 20, 200, 2,000. You can see that there's a whole range of distances in pipe diameters for laminar flow. That's why this one's so easy when it's turbulent, just 10D. All right. Well, I need to develop a review of fluid mechanics and develop that laminar velocity profile. So let me back up here and do this. What would be our governing differential equation to help us solve for U as a function of R, where R goes between 0 and cap R? Well, it would be our momentum equation. Our momentum equation, and in the fluid mechanics, you get the viscosity divided by R, the derivative with respect to R of R, the change of U with respect to R, is equal to the change in the pressure with respect to X. So the pressure is a function of location X. Often it's going down, it's high pressure, and it's lower pressure in the direction of flow. So what is dP dx? If this is the x direction, that's negative. It's less than 0. It's negative. Okay, so that's what this term is. What is U right here? That's our velocity. We're trying to find U as a function of R. What is mu? Not to be confused with U. What is that one? Our viscosity. And then so this is our differential equation. What would be our boundary condition that the velocity profile, when it's fully developed, it's the center line where R is equal to 0. It can't have any slope. So the du dr at R equal to 0 is 0. one way to say it is symmetrical, the top half, the bottom half of the pipe, but that really doesn't make much sense. It's a 2D slice that I'm showing, but it has to have a zero slope right there at the tip, at R equal to 0 at the center line. The other boundary condition is that U at cap R is equal to no slip, 0. You're all set up. So let me do this because this could be on the next test, just like I asked another similar question like this on the last test, didn't I? How do I solve this mathematical problem? So you separate and integrate. So when I separate, what I'm going to do is I'm going to take these two terms and bring them to the other side, as well as this term, leaving only the derivative of R, well, the change in R du dr equal to, this is just a constant, dp dx, just leave it alone. Treat it as an entity all by itself. We talked about it being a negative. When it's fully developed, it's just a constant value. You're not changing the diameter of the pipe as you're going down. Viscosity of the fluid's not changing. It's a very simple system we're working with. So that's just a constant. And then you put over here, you put in the R over mu dr. That's the separate part. Hopefully that's understandable. Then you do the integrate part. The dp dx is a constant, comes outside the integral. The 1 over mu comes outside. So, but just put it like this. Okay, so now when you integrate, you get that R du dr is equal to dp dx over mu 1/2 r squared plus a constant of integration. Now, some people put the play with the limits. They put here and then they go out to an arbitrary r, from 0 to an arbitrary r. That way you don't fool with the constant of integration, but either way works. There's a couple different mathematical approaches. At this point, I look at my boundary condition and I apply that boundary condition. Why? Because I see right here is du dr. And so it's like, let me kind of scoot down a little bit. So if I apply that boundary condition at r equal to 0, it's like 0 times 0 is equal to, then I have dp dx 1 over mu 1 over 2, 0 squared, all that goes. And so what does that constant of integration have to be? Drop it, get rid of it right away. So, okay, now we'll continue that work. Let me just kind of go up here. So we conclude that this C is equal to 0 from that first boundary condition. Now we have to continue to separate and then integrate. So what we're going to have is du is equal to, I'm going to put, let's do this, dp dx, the 2 mu like that. Okay, and now we're going to have the r dr. Hopefully that's you can follow that. Now we're ready to integrate, and we pick up u is equal to dp dx 1 over 2 mu 1/2 r squared plus another constant. You could call C1, C2, whatever. Okay, at this point you can say, what is my constant? Well, apply the second boundary condition. U at cap r, or lowercase r equal to cap r, the outer radius, is equal to 0. So 0 is equal to dp dx 1 over 4 mu cap r squared, or C is equal to a negative of all that. And what I like to do, as soon as I have that negative sign, I like to lump it with dp dx. And then I know that negative dp dx is a positive entity. Because if I know this is a review of fluids, but this is a negative, so I keep the negative with the dp dx. Your choice, either one. So what is the solution then? It's u is equal to, and then you have this cap r squared minus dp dx divided by 4 mu, and then you have the 1 minus r divided by cap r squared. Now that's your quadratic profile. So what's the maximum? Well, it's at r equal to 0. So the u max is equal to the r squared negative dp dx divided by 4 mu. That's u max. So you could replace it. You could say that u is equal to u max times 1 minus r over cap r squared. Kind of a classic result, laminar flow. Too bad most pipe flow is turbulent, but it's nice to have an analytic solution. All right, once I have the description of the velocity profile, u is equal to u max 1 minus r over cap r squared. How do I calculate that mean velocity? Mean velocity. Well, what's the criteria for the mean velocity? Because we're going to get to the mean temperature. And when we get to the mean temperature, we're going to scratch our head and say, well, what was our concept that we used for the mean velocity? So what you want is you want a simple equation where you say the mass flow rate is equal to the density of the fluid, some mean velocity. They put a subscript m on the velocity for mean velocity. This is u sub m times some area. Well, what's the area of a pipe? Pi d squared over 4. Isn't that our flow cross-sectional area, pi d squared over 4? That's what we really want. We want a simple equation where we use that. But how do I calculate that m dot if I want to do the integration? So I think about my pipe, looking at it, there's a center line, and I take little strips. What do you mean a little strip? Over this little area right there, it has a constant velocity, the same velocity. Okay, so if I said I'll take that velocity at that location r, I'll multiply by the size of that little red strip that I have. What is that size? 2 pi r dr. What's 2 pi r? That's the circumference, and then dr gives it the width, so I have a little area. Okay, that's like a little dA right there. So u dot dA, that's what I'm building on. If I multiply by rho, I turn that volumetric flow rate into a mass flow rate, and then I'm ready to do the integration from lowercase r equal to 0 to uppercase r. So this is how we would calculate the mass flow rate using the velocity profile by integration. This is how we'd like to calculate the mass flow rate using a simple mean velocity. So it's like m dot is equal to m dot. So we're going to have rho, what we want to calculate, a nice equation for the mean velocity, times the area pi d squared over 4 is equal to the integral rho. U is a function of r, which I can now substitute, put u max times 1 minus r over cap r squared, 2 pi r dr. Now, once you set that up, you can do a lot of simplification. our density is not going to, it's a constant. I know that somebody could say, well, my density varies in the middle of the pipe. It's more dense than at the wall of the pipe. Great. We don't want to consider that. It's simple. And then the pi's can go. And you can play around with the 4, whatever. But what I can do is I can divide over by, here, put a 4 there, get rid of that one. Come over here with that, here. Forget I like to work in diameters. How about this one? Pi r squared instead of the pi d squared over 4. That way I'm done with the 4. And I like this better. Now I can bring that r squared over, put a cap r there, put a cap r there. And so u sub m is equal to u max times the integral of 1 minus r over cap r squared times, I'm going to put, where should I put that 2? Well, I'll put the 2 right here. 2 times r over cap r times the derivative of r over cap r. Or from your calculus, you can say, well, let's let this 1 minus, I don't know, you want to call it tau squared times tau d tau, d tau, where tau is r over cap r. And then I integrate from 0 to 1. And then I have 2, and I have u max, u m. All right, how would you do that integral? Well, I'd explode it a little bit. Let me scoot down here a little. Wouldn't I put here tau minus tau cubed, d tau? And now I integrate. Okay, I can do the first one. That's just 1/2 tau squared. How about the second one? Minus 1/4 tau to the 4. Did I do that okay? Then I evaluate this at 0 to 1. So I get a 1/2 minus a 1/4, which is a 1/2. Did I do that okay? I mean, sorry, a 1/4. Yeah, a 1/4. Thank you. You're paying attention this morning. Good. Then I have the 2, the 2, the 2. Now I get the 1/2. And then this is my u max, my u max, my u max. And you get the very common or familiar result that the mean velocity for a laminar profile in a pipe is 1/2 the maximum. 1/2 the maximum. So this is only laminar. Somebody says, hey, I have a pipe flow, and instead of being laminar where I have this nice quadratic shape, it's turbulent. What's the turbulent profile going to be? Steep, plug, steep, right? That's kind of the shape of it. It's pretty flat. I know now we have to talk about, because it's turbulent, a time averaged velocity at each point radially, and it'll be like that. In this case, the maximum is over a broad range, not just at the center line. And the U mean is maybe not 0.5 of U max, but maybe 0.8 or so of U max. It's going to be higher than 0.5 if it's turbulent flow. And you can work out, and you can get an analytic velocity profile to some power, make it look like that, and then do the math and find whatever coefficient it is. But it's higher than 1/2. All right. Well, that's what we just did. All right. So we have this pressure gradient. So if I have my pipe like this, all right, trying to draw it and help you see things. And on this face I'm making a little control volume out of the pipe. Okay, so it goes and goes and goes, but at this cut, I can talk about the pressure in the fluid. And if I focus on a particular control volume, CV right there, all right, that little control volume has a pressure force, or pressure times area gives me a net force, and it's pushing it in the direction of flow. This is the direction of flow, like that. So it's pressure is pushing like that. So I have the pressure at the location X. I have also the pressure at the location X plus delta X. This distance is delta X. Okay. The pressure on the surface area at X plus delta X, it's a little funny, but what direction does that pressure push? It's always pushing inward, right? It's always pushing inward on our control volume, so it's pushing back up. So what I'd like to do is say, for this control volume, I have a fluid shear stress at the wall. What does the wall do? What type of shear stress does the wall induce on the fluid control volume? And it's in this direction. How would I draw it? Like this. And I put the tau at the wall. So it's a force per unit area, just like a pressure, but it's a viscous shear stress. And it's what the non-moving wall applies to the fluid in the control volume. Professor, how come it's not the other direction? Well, it's because it's friction's retarding the direction of flow. The direction of flow is this direction. Or it's opposite, not retarding, but it's opposite. So we do a force balance. Free body diagram, if you like that, if you're thinking about statics, or if you think about fluid mechanics, whatever. It's a force balance. So the force balance says that I'm going to have the pressure at X pushing in one ray in the positive X direction. In the negative, I have the pressure at X plus delta X. It's in the negative, so I put a negative on that. And I multiply by the area. You can put, I like to work in diameters, pi d squared over 4 instead of radius. More common to talk about the diameter of a pipe than a radius of the pipe. Anyway, and then that's going to be the net going in the positive direction, down the direction of flow. Maybe I should have introduced X, put X like here. There's X. Okay, and then what do we have in the opposite direction? The wall shear stress. And then you have to think, okay, what is my perimeter? 2 pi r or pi d times delta X. So what's the point of this is you get, well, do this. Divide over by delta X. So those cancel. In the limit, what does this become? As delta X gets smaller and smaller and smaller, this becomes negative dp dx. All right. We can cancel some other terms like the pi, one of the d's, and then we get that the wall shear stress is equal to the negative of the pressure gradient, and then you have the diameter over 4. Okay. So they're related. Because of friction, you get the wall shear stress, and if you want the fluid to flow down the pipe, it's gonna go from high pressure to low pressure, and there's gonna be a drop in pressure, pressure gradient going down. Okay. From our previous, where we had external flow, there was this friction coefficient, the coefficient of friction, C sub F. What was it defined as? Well, we had the wall shear stress, and we normalized it. We normalized it by 1/2 rho U squared. Sometimes if it was external flow, we talked about U infinity, but here we have the internal flow in a pipe. What's our fluid velocity, our single velocity of interest that makes sense? our mean velocity in the pipe, right? So 1/2 rho u mean squared. So now you can replace, and you say, oh, well, the friction coefficient is negative dp dx times d over 4 times 1/2 rho um squared. In fluid mechanics, we have F, and often the book doesn't do it, but I'll put a subscript D on that, and that'll be a friction factor, a Darcy friction factor, sometimes a Darcy-Weisbach friction factor, and I just butchered that name, but there's different names for it. But it's a friction factor in the most Moody diagrams, not all of them, most Moody diagrams. And so then you're looking at, and you say, well, what was the definition of that friction factor? It was like negative dp dx. You had the d, and you had the 1/2 rho um squared. And you say, ha, that 4 is missing. But if you take the C sub f, and you multiply it by 4, you'll get that friction factor. And so this is very confusing to a lot of students in the literature. It's like, hold it, we have like 2 friction factors out there, and they're different by a factor of 4. Just, either divide by 4 or multiply by 4. Okay, and this one is the Darcy, and sometimes they'll call this one the fanning. I should put a cap F. Darcy fanning. I think most people are more common. This one is a little more common. All right, let's see if we can find the Moody diagram. Okay, so I just put up here, what do they call it, the Moody diagram? Well, because when students look at it, their mood changes. They go from happy to sad or sad to happy. No. After somebody who published it, and they correlated a lot of work. Have you seen this diagram? You bet you've seen it. You can't go through any fluids class without it. Often they'll put it in a book, they'll put it on inside jacket cover or somewhere prominent. All right, so what's on the x-axis of the Moody diagram? Reynolds number. Is it a linear or log scale? Log. You're covering a lot of terrain. And so way down here is what's at 1,000. Hey, we're below 2,000. We're in the laminar region. But you know what? That's the whole laminar region. What's above? A whole lot of real estate devoted to turbulent flow. All right. What's on the y-axis? Well, it's that friction factor, F. Look at the definition. Is that my C sub F, like a fanning? Or is this a F? Maybe if the author wanted to add a subscript, they'd add a D for a Darcy. It's our Darcy. This book doesn't make a big deal of that, but it's just an F without it, without any subscript, and you can look at it and there's no 4 in there. Okay, so now take a look at this. Log or linear on the y? Log or linear? This is a little harder to tell, isn't it? Because this was, hey, 10 to the 6, or whatever, 10 to the 5, 10 to the 6, 10 to the 7, 10 to the 8. What about this one? Who says linear? Who says log? Looks like the logs have it. It's log. It really is. You have to stare at it a little bit, but take a look. Here is 0.01. I go up by a factor of 10. That's 0.1. Where is 0.1? Right there. Could they have put this linear? Sure, but they didn't. It's log. It's common to put it log. Okay, so it opens it up a little bit. But if you look at it, what is the change from here to here, from 0.09 to 0.1? What does that change? 0.01, isn't it? All right, come down here and say, if I'm at 0.01 and I want to go to 0.02, that's a change of Oops, that's 0.02 right there. That's a change of 0.01. So this is the same amount of change versus this one. So that's why it's a log scale, to help you see it's a log scale. Now, somebody says if you're above on the x-axis Reynolds number, you could be 10 to the 4, 10 to the 5, 10 to the 6. I mean, it's pretty far out there to get 10 to the 7, 10 to the 8. There's a whole lot of applications in this range, engineering applications. Okay. Look at the friction factor. Somebody comes in and they says, I just calculated my friction factor and it's 0.0001. Guess what? It's not on the diagram. It's too small. Somebody else comes in, oh, my friction factor is 2.13. Really? We need to check our math, because where are we at? We're over, it's too high. So anyway, I mean, between 0.01 and 0.1 is the vast, vast, vast majority of applications. Okay? All right. Hopefully you see that. Actually, you could even tighten it down even further. But that just limits it. All right. So now we have this region, laminar flow. The friction factor is a constant divided by the Reynolds number. If you are using the fanning C sub F, it would be a 16 over the Reynolds number. If you're using this friction factor, it's 64 over, what's the difference between 16 and 64? I have to multiply 16 by 4. Again, that 4 comes up to get that. Okay, so some books you'll look at it and say, hey, they got a typo, they put a 16 there. Well, they have the other friction factor. What can I say? Okay. Sometimes they'll put a kind of a mushy cloud like this, and that's, where is the data going to fall? Anywhere in this region, there's this not just transition, because they call this a transition zone as well. The transition zone really is everything here. And then they have different names for it, but this book puts fully rough zone. What? Do you remember this when you're looking at the Moody diagram? Fully rough. Sometimes they'll say fully turbulent zone. But what's special about all of these curves, which show you different relative roughness? This is a relative roughness of 0.02, right? Goes like this. And then it hooks up. What's common about all of those red lines in the fully rough zone? Just make that observation. A 6th grader could make that observation. They are flat. They're flat. So you come over here, and often you're thinking about using this Moody diagram to get the friction factor, and I have to get it as a function of, give me 2 pieces of information, give me epsilon over d, that's the relative roughness, and give me the Reynolds number. Okay, so right here is our relative roughness. Maybe it was 0.02, maybe it was 0.00, whatever that is, 0.002, maybe it was really small, maybe that's a smooth pipe. This is all right down here is smooth. I should emphasize that right here for smooth pipes. And there are a lot of applications of smooth pipes. If you're doing PVC, you're doing copper, it's pretty smooth. Just take a look at drawn tubing, very low roughness. Down here they give you roughnesses. Drawn tubing, and you look at some diameters, and you're going to get very low relative roughness, essentially smooth tube. Here's commercial steel, here's cast iron, and here's some concrete pipe. So anyway, a lot of books will have even much more information. Okay, this is a relative roughness for this type of material for this condition. Okay. But what about out in this fully rough zone? The lines are flat. Does that mean it's only a function of Reynolds number? The friction factor is only a function of Reynolds number? Or does it mean that the friction factor is only a function of the relative roughness in that region? Which, A or B? In the fully rough region, is the friction factor only a function of Reynolds number? Answer A. Or is it only a function of the relative roughness? Answer B. You ready? Which one? Go ahead. B? B. It's B. It takes a while to stare at it, and it's not that intuitive, but just do this. Let's say that you have this roughness of 0.002, and you had this friction factor of 10 to the 6. And, oh no, now we sped it up. Now not the friction factor. The Reynolds number is 10 to the 7. Did it change? Did the friction factor change? No, it's the same 0.05. Okay, but if you're at 10 to the 6 right here, and this relative roughness, and they say, no, we're going to switch it out, we're going to go to a smoother pipe, and now the relative roughness is down here. Well, you just changed the relative roughness for the same Reynolds number. Did the friction factor change? Yes, it did. So out in this region, it's only a function of the relative roughness. That's a big deal, a big conclusion, because a lot of times you'll see that, and it's like, hold it, that friction factor is not a function of Reynolds number. The analyst has concluded it's out in the fully rough region, and there you go. All right. Now, in this region, guess what? You're a function of both. What about here? Laminar flow. Well, do they have multiple curves for laminar flow for different rough pipes? Nope. They just do it only for the smooth pipe. Yes, sir.
So say you're going through the problem and you get a crazy high friction factor. How do you know if that's a mistake or if it's fully rough?
If you're above, let's say in this vicinity, 0.07 or something, it's a red flag. If you're in the 0.05, you're good. There's a lot of cases out here. So now I have seen it where I think I looked one time, I did some analysis of a mine, airflow through a mine shaft. And when you look at a mine shaft, it's really rough. And it was above this typical pipe chart. This is for pipe flow. So you can get some sort of equivalent friction factor for some crazy applications like that are higher. Well, I think I spent a lot of time on the Moody diagram. Hopefully that was a good review of your fluid mechanics background class. Very important. So that Darcy friction factor, what was that? That was on the y-axis of the Moody diagram. All right. Now, what is it defined as? F is defined as negative dp dx times d divided by 1/2 rho um squared. Did I do that correctly? So if you have a pipe like this, and this is the inlet, and that's the outlet, and you have the pressure in and the pressure out, okay? The pressure out's lower, and so the pressure in minus the pressure out is the pressure drop. And often people want to calculate that pressure drop. Well, think about it. Here's your pressure as a function of location x. It goes from 0 to L, the length of the pipe. And so go slow, but this negative dp dx, all right? I'll just work on that for a minute. Negative dp dx. So if I do this, I'm going to do the L minus 0, or maybe I should do this one, x2 minus x1, and then p2 minus p1, and then put a negative in front of it. Okay, let's talk about location 1, location 2. So what is x of 1? 0. What is x at location 2? L. Okay, and then what is the pressure at 2? That's my pressure out minus the pressure at 1, the pressure in, and I have L minus 0. And so what you get is negative dp dx is my pressure drop, P in minus P out, divided by the length of the pipe. So how do you unravel and use this equation? Often you do it like this. You say, hey, my pressure drop is equal to the friction factor, length of the pipe normalized by the diameter of the pipe, times 1/2 rho um squared. What's this? It's my velocity pressure. What is this? It's how long it is compared to the diameter of the pipe. What is this? My friction factor. So this is the way I kind of remember a lot of this. Is the pressure loss is F L over D times 1/2 rho U squared. All right. That's what we just did. Should we solve a problem or two? So we have water at 27 C. Convert that to Kelvin. 300 Kelvin, good. It's flowing with a mean velocity of 0.15 meters per second. So use of m is 0.15 meter per second. Through a ridiculously long L of 576 meter long cast iron pipe. Why did they give us cast iron? Because you go to the Moody diagram or some other source and you get that roughness of cast iron. Okay. And the inside diameter, D, is equal to 0.15 meters. Okay. What is the value of the viscosity of the water? Or is it the viscosity of the cast iron pipe that we're in? No, it's not. It's the water flowing in the pipe. Come on now. So how do you calculate that? So you just have to get the right table. In our textbook, we have table A6. Hey, one of the exam problems was simply getting data out of a table, and what I wanted to see was, and that's why I'll look also at your homework portfolio and say, hey, how come you got the data out of the table perfectly for the homework, and yet on the exam, you botched it? I don't understand. But what you have to worry about these factors, this 10 to the 6 and 10 to the whatever, 3s and other things up in the header, don't you? All right. So what we're interested in is viscosity, and this is for saturated water. You could get the steam or the liquid from thermo. So we want the liquid, and we're at 300 Kelvin. And so here it is. And if you just put, hey, it's 800, and what is that, 55? Then you said Newton second per meter squared. Would they be correct? Or what did they forget? Oh, we just ignored that 10 to the 6. No. So, this is the clicker question, like, what is it? How do I adjust? Is it 850, 1, 2, 3, 4, 5, 6, move it over, like that? Is that what it is? No, it's not that. You're right. So it's 1, 2, 3, you move it over, pop, 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 pop. So it goes right there. 0.000855. What's the value of the surface roughness in meters? How are you going to get that one? Well, you have to have something like the Moody diagram. And what did we say it was? Cast iron? And here it is. What's that number? 280? 260? 260? All right, so can we just ignore this? What's that little mu sub m? So it's 0.00026 meters. All right. And then what is the Reynolds number for this problem? Well, the Reynolds number is rho, my mean velocity, which is given right there, the diameter, which is given right there, divided by mu, which we just looked up for part A, or the first part of this problem. So the only thing is I have to get the density. It's water. It's going to be around 1,000. But if you wanted to go to this table right here, you could get the specific volume and reciprocate it to get the density. And so it's like this number, but they have the 10 to the 3, so the specific volume of saturated liquid water is 0.001033 units meter cube per kilogram. I reciprocate that, it's about 1,000. 997 or something like that, kilograms per meter cubed. Okay, for this problem, 26,200. What does that tell you? Turbulent flow. Turbulent flow. Often I like to put a 2.6 times 10 to the 4 because it's easy to misread on the x-axis of the Moody diagram and be off by a factor of 10 in the Reynolds number. So there you go. Okay, what's the value of the friction factor? Well, I got ahead of myself. I need to now go to the Moody diagram, find this on the Reynolds number. I have my roughness, so I then need to get a relative roughness. Get a relative roughness. Find my relative roughness curve at that. Okay, so what is my relative roughness for this problem? I should, where's my number for that? Well, I have it on this slide right here. All right. The relative roughness comes in at 0.00173. 0.00173. So can you write that down? Where is 0.00173? Between this one and that one, right? So we have to do a visual interpolation. Maybe I change and I just put it right there and I kind of draw it. 0.00, oops. Yep, got off on the wrong one. And then what was my Reynolds number? 2.6 times 10 to the 4. Here is 10 to the 4. Here is 2 times 10 to the 4. It looks like right around here. All right, so I'll say they intersect right there. And we'll bring it over. What do you pick up for friction factor? 0.02. Now we're going to quibble a little bit. 0.028. 0.027. I don't think it's 0.029, right? Okay, so there you go. Yes?
So for the homework, I'm a little bit worried about 1 plus. Is there interpreting everything from the chart?
You don't have to. So let me see if I have it here. You can read from the chart. You can't get any better than 0.028. Just, your eyes aren't that good. Now, you can use the Colebrook equation and iterate. I can show you that if you're interested in Excel. They're going to use the Colebrook and interpolate or iterate or something inside. Or there's another one. If you want to look it up, the book doesn't talk about it. Churchill, no iteration required. Colebrook was older. Churchill equation, it's out there. All you have to do is type it up. I think I did it right here. I have it built in. I don't know if I built it or got it off the internet, but friction _ Churchill. You feed it 2 pieces of information. You feed it the relative roughness, and you feed it the Reynolds number. And it spits out the friction factor. What is that? 0.0284 from the Churchill. And then if you want to do the Colebrook, here is the equation. I don't know if you can see it that well. Whoops, I made it distorted, didn't I? But you have the friction factor here, square root, and you have the relative roughness, and that's log base 10. So what I do in Excel is I say, I'm going to guess the friction factor. Maybe this one is to start it with is 0.1. Okay, if I put it into the Colebrook equation for that Reynolds number, that relative roughness, the right side is not equal to the left side. So basically what I did was I took this part of the left side, put it over on the right side, or right side to the left side, and you get an equation equal to 0. You need to do root finding. Numerical methods class you took, right? You get the root. And so you want to drive something to 0. Currently, that something, well, escape right here, is, you see what I did, 1 over the square root of blah, blah, blah cell. You grab cell B8, which is my friction factor, and I just coded that up, the Churchill equation, but I made everything on one side. I want to drive that to 0. Excel under the data tab. This is the data tab. You go under the data tools in this part right here. And maybe if it would be a bigger screen, you could see it, but it's a GoalSeek. You got to find it. How many people have used GoalSeek? A handful? It's pretty useful, isn't it? Once you get used to it, there's a lot of applications for it. And what you do is you click on this one and you say, I want to drive this to 0. So you come under here and you say, GoalSeek, okay. I'm at the cell, what is that, B9, and I want to drive it to a value of 0. You could drive it to a value of 5 or 10 or 99, whatever you wanted, the GoalSeek. This is just a tool. And by changing only one cell, and I'm going to change my guess of the friction factor. I guessed it P.1, and then you just go there. So it came in 0.0281 from the Colebrook equation. All right, look okay. So I'm sure that either in Wiley Plus they have something like the Churchill equation, or they're iterating with the Colebrook, or they only have so many sets of parameters, and then somebody went in and for each one of them hard-coded what the friction factor is for this Reynolds and relative roughness. But the Churchill equation is not that hard to code up. Okay, let's jump back. Professor, when are we going to get to some heat transfer? Patience, patience. All right, what's the pressure drop in the pipe? Well, we use our pressure drop equation. That's the friction factor we worked so hard to get, the length divided by the diameter, and then the 1/2 rho u mean squared. And you can calculate it. And for this problem, you get so many Pascal. Watch your units. You want to convert that to bar? No problem. 1 bar is 10 to the 5th Pascal. All right. All right. That was all fluids. You can get this equation, the friction factor, 64 over Reynolds number. It's more algebra, just repackaging. Okay? So done with that. You can, again, emphasize the difference between the Fanning and the Darcy friction factor, that factor of 4. And often the red flag is if you see that it's, in the Moody diagram, 16 over Reynolds number in that laminar region, you know what friction, that's a different friction factor. It's not 64. Okay. Fluid. Okay. Maybe I don't know. I don't know if I should build this. Somebody says I have an electric motor. Forget that it's 3-phase, and forget that there's a power factor. The most simple equation to calculate the electric power, here's a plus and a minus line, right? Hot and ground, is to know the voltage and the current. So you would get the W dot electric. What do you mean by W dot? It's electrical power being supplied to the electric motor. What is it equal to? It's the product of? Yeah. So it's the voltage times the current. How do you know that? Somebody said, prove it. I'd have to go get a book or something. Give me access to dictionary or encyclopedia. But you just use it so often, and when you have this in, maybe I should have used E for the electromotive force, and it's measured in volts, and then I is the current measured in amperes, and 1 volt times 1 ampere is equal to 1 watt. How do you know that? You're just brilliant, you know, you just solve these problems. Okay, the electric motor has a shaft coming out of it. True? The shaft is rotating and spinning at a certain rotational rate. What do you want to call that? What symbol do you want to use for the rotational rate? Maybe you did alpha, maybe omega, or n, the speed, rotational speed. What would this omega be in units of if I said n maybe in revolutions per minute? But if I think of the angle theta, and I'm going to measure the angle of rotation in probably radians, you're exactly right. And so what would be the next step of the derivative of the angle with respect to time? That would be my omega. Wouldn't that be radians per second? And there's power being transmitted in that shaft. What is the force, so to speak, in a rotating shaft? It's my torque. Torque. What symbol do you want to use for torque? Tau. Give me the units of torque. Newton meter. You know, one time I had a Thermo 1 problem, and I said, okay, this is the first test, Thermo 1, and I said, I want you to calculate the torque in the shaft. And everybody came back, not everybody, but half the class came back, and maybe I wanted the answer to be 110 Newton meters torque. And they came back with 110 joules. And I was left with a big dilemma. What do I do? Do I say, okay, you're a brilliant student, you're right, you can march out of here with a degree in mechanical engineering, and you can report your units of torque in joules. And you'll be laughed up and down wherever you go. They're not wrong, are they? Isn't a Newton times a meter a joule? What would you have done? Give them full credit? I took a point or two off and let the howling begin, because they were like, hey, a Newton meter is a joule. I learned it. I'm confident of it. Yes, you're right, but that's a unit for energy. Torque, let's just do it. Everybody that I know of, every book that I know of, does not have torque in joules. It's a Newton meter. Thank you. Hopefully, I don't know why, but that only happened one time. It seemed like crazy semester. I don't know who they had for physics. Okay, now, what is my W dot in the shaft? I have a rotating shaft. It's transmitting, you know, that it's the product of omega times. This is incredible. How do you guys know all these things? All right. Now I put it into a pump. And the pump takes a fluid in and a fluid out. And something changes because, and it's water. It's just a water pump. No, don't make it any complicated. What changes between the inlet and the outlet of the pump? Does the density of the water change? No, it's incompressible. What changes? The velocity of the water? Does the velocity of the water change from the inlet to the outlet of the pump? Let's say I have a 2-inch diameter pipe on the suction and a 2-inch diameter pipe on the discharge. Did the velocity change? No. What changed? The pressure. So what we have is we have the pressure exit minus the pressure inlet, or the delta P. Hey, what SI units do we like for pressure? Oh, I know we could do bar, but let's just do Pascal or kilopascal. Okay. What is my equation for the W dot that's getting into the fluid? Maybe I purchase 100 watts of electricity. That's electric power. maybe the motor converts to 95 watts of shaft power. And then I feed it into a pump, and I'm going to maybe get 80 watts of something. See what I'm doing is you got this conversion of energy from one form to the other, electric to shaft to fluid. So what is my equation? You remembered E times I pretty well, and a volt times an amp is a watt. You remembered radian per second, rotational rate times a torque, and then you report that watts. No, hey, this is great. What's it for the fluid? The pressure gain, and I could put gain here to be, because a pump doesn't lose pressure. The frictional losses in the piping, but it's a gain in pressure across a pump. Okay, times what? Times what? Somebody show off. You know this. It's a fluids. Review of fluids. Okay, do this one. Pascal is a Newton per meter squared. I'm going to have a Newton per meter squared. I want to multiply that by something to get a watt. What is a watt? A joule per second. True? Just like those Thermo 1 students a couple years ago, they know a joule is a Newton times a meter, isn't it? Okay. So can you tell me what do I need to multiply by to get this equation to work? I get a meter cubed per second, isn't it? What is that? That's a hint to what we're looking for. Volumetric flow rate. Not a mass flow rate, a volumetric flow rate. So what's our symbol? A lot of times we use Q. Maybe you put m dot divided by rho. I mean, there's a lot of symbols here for what the volumetric flow rate. What's your favorite volumetric flow rate symbol? Q? Q? Yeah. Oh, that's another one, right? Like this. Volumetric flow rate. That's a good one too. You have to remember the pressure gain times the volumetric flow rate gives you the fluid power. All right. What happens if you want to just do a curve fit in a limited region? Well, they have a lot of people worked in fluids, and they come up with the Blasius correlation. There's a lot of these correlations for turbulent flow in a smooth pipe where the Reynolds number is less than 10 to the fifth in this region right in here. Nice, simple equation. All right. Well, there was a lot of review of fluids, wasn't it? How about thermal considerations? Well, we have to come in and talk about a mean temperature, just like we talk about a mean velocity. Then you have Newton's law of cooling. That's just Q double prime is equal to H times two temperatures. Okay, so we're talking about pipe flow, internal flow. I'll talk about maybe the hot wall surface here. What do you think is an appropriate temperature for the fluid? The mean temperature of the fluid? Absolutely. So that's perfect. And this is into the hot wall, into the colder fluid. And then you have these fully developed conditions. What do you mean by fully developed? In pipe flow, you have a velocity profile that could be developing, and you could have a temperature profile that could be developing until it becomes fully developed. All right. So let me continue on. So thermal considerations. Thermal entry length. Here's our pipe. And after a while, we'll have to be fully developed, not hydrodynamically, but thermally. It depends on laminar flow or turbulent flow. This one's very easy. Hey, what was it to be fully developed hydrodynamically if you're going to have turbulent flow? The distance to be fully developed hydrodynamic was, do you remember it? 10. That was probably your favorite year when you were that old, 10 years old. How many remember 10 years old? You're probably champion at 10 years old, right? Maybe you only got better at 11 or 12, but 13 it went all downhill. Well, guess what it is to be fully developed thermally? I said this was easy. 10 Ds. Why? Because the mechanisms to mix it all up are the same for the velocity or momentum as well as the energy and the heat. Okay. Laminar flow. To be fully developed hydrodynamically was 1/20th of the diameter times the Reynolds number. All right. Guess what? Fully developed thermally, it's 1/20th. I like the parallel here. Diameter, I like the parallel here. The Reynolds number, I love it. But they have to change it up a little bit, and they throw in a piece of R. What is PR? Prandtl number. Prandtl number is nu over alpha. Is that correct? And it's how the momentum diffuses and the heat diffuses. So that's the equation for it to be fully developed thermally. So you get the 1/20th diameter Reynolds Prandtl. This is the distance to be fully developed hydrodynamically, and then you scale it by the Prandtl number. If the Prandtl number is large, then it takes longer to become fully developed. If it's short, what's the Prandtl number for air? 0.7. That's close enough to 1. Round it off. How about water? It ranges 2 to 8 to 6. You know, it's greater than 1, up to 10. Okay. All right, what about this mean temperature? How did we get the equation for the mean velocity? We had something simple, then we had some integration. And so if somebody says, I want you to calculate the average energy flow down a pipe, you'd say, well, I need to know the velocity at that location, so U is a function of R. Thinking about a ring again, here's that ring. They have the same velocity. I'm going to also say in that ring it has the same temperature. So then I have the velocity times the little dA. What does that give me? A volumetric flow rate. What was my dA again? 2 pi r dr. All right. So I have my volumetric flow rate. I multiply by rho. Isn't that my mass flow rate? So we went back to where we were, but now I need to think about energy flowing. Energy flowing. Well, if I multiply by specific heat and then T minus T ref, REF, reference temperature, what would that tell me? It would be the energy content of the flowing fluid. Somebody says, well, that's going to integrate over the entire area, or integrate from 0 to cap R, rho, C, U, and then this T minus T ref, that's a constant. You just put T in there, just multiply by T. The reference temperature will drop out, so simplify. All right. What about over here? Well, I have the same mass flow rate times specific heat times the temperature, and I'm really interested in the mean temperature. This gives me the equation for the mean temperature. That mass flow rate would be rho UMA. Isn't that the mass flow rate? And so the mean temperature equation is, look at the specific heat and density are often just, I mean, you can have a complicated problem, but they're constants. So throw them out, cancel them on both sides. You'll have 1 over the mean velocity, the cross-sectional area, the integral from 0 to R of U, T, 2 pi r dr. At this point, it's probably better to say What is pi r squared? Isn't that my area? Cancel the pi's. Bring this cap r. We did this before. So maybe you have a dummy variable of integration, tau or x or something else. And if you put in your laminar velocity profile there, you can calculate the mean temperature. If you put in an approximation for the turbulent profile, you could analytically calculate the mean temperature. All right. Well, luckily, this equation may be a little complex to understand, but it's really simple. If I had a pipe, and let's say the pipe wall is hot, and so it's the fluid close to the pipe wall is red, indicating it's warmer, then in the middle of the pipe, the core of the pipe, where I color code it blue, indicating it's a little cooler. Let's say you took 100% of the flow in the pipe, diverted it for 1 second into a container big enough to hold it. So it all dumped in to a container. The container is perfectly insulated. It mixes the stuff that was near the edge, but it's flowing slower at a lower speed, isn't it? The colder in the middle, but it's flowing faster. It perfectly mixes to come to an equilibrium with one temperature. Guess what that temperature is? The mean temperature. It makes sense. All right. Sometimes they'll call it the bulk temperature, the mixing cup temperature. It's the mean temperature. All right. Fully developed pipe flow with a constant surface heat flux. So here is my pipe. All right. Forget about the entrance region. At this point, I'm just saying X, it's fully developed. And if you have a constant surface heat flux, what's happening here? Q double prime is a constant. Not the wall temperature is not constant. Q double prime is constant. How could you experimentally achieve that in the lab? Take electric resistive wire heater, wrap it uniformly over the pipe all the length, and then turn it on. And so you just wrap a wire over the pipe, insulate it on the outside, turn it on, and it's basically going to push the heat. Q double prime is constant. Okay. So let's plot our mean temperature. Here's our temperature axis. Let's say it comes in right here, I don't know, 30 degrees C. That's TM. TM on the inlet. Does it stay 30 degrees C throughout the pipe? Does it get colder? Does it get warmer? What does the mean temperature do as the fluid is flowing in that direction down the pipe? This is where it comes out of the pipe. What's it going to do? Isn't it going to do that? Now the question is, does it do something crazy like this? Or does it do something crazy like that? You know, is it concave up, concave down, or just a straight line? Why is it just a straight line? Because for every foot, I'm getting the same amount of heat added. For every inch or foot or meter, I'm getting the same amount of heat added with a constant heat flux. All right, so that's our plot of TM. Somebody says, can you calculate the exit temperature, TM at the exit? Sure. You would do energy balance conservation. You'd basically say, how much area do I have? You would have the area would be pi d times L. This is 0 to L, pi dl. Multiply that by Q double prime. So Q is equal to Q double prime times that area. That's how many watts are coming in. What's it going to affect? It's going to raise that mean temperature. It's going to be the mass flow rate of the fluid in the pipe, the specific heat, and then the change in the mean temperature, the Tm at the exit minus the Tm at the inlet. Call this state 1 inlet, state 2 exit. That's equal to, I got too many equations here. Put the A up here, pi dl, that's Q. Make sense? Yeah. Okay, what about the wall temperature? Well, if it's fully developed, you're basically going to have H is going to be a constant. The convection coefficient's a constant. If the convection coefficient is very, very high, large, then you're going to have the wall temperature is close to the mean temperature. It's going to be a little higher, but it's going to be close. If H is low, then it's going to be a greater temperature difference. And so everywhere at this point and this point, there's a temperature difference, isn't there? And because it's all fully developed, that temperature difference, the T of the surface minus the mean temperature at that location, is a positive amount, and it's constant. So from our rate equation, Newton's law, if I took this multiplied by H, isn't that Q double prime? Being forced in. All right. Well, life only gets worse when you have to consider developing or entrance region. It's easy when it's fully developed. The surface temperature is flat, the mean temperature is flat, there's a uniform same delta T between them. But if it's in the entrance region, right in here, the mean temperature is still flat because the flux is constant, but the delta T gets smaller at the entrance. Why? Because the local H, the local convection coefficient's higher. It's kind of a ripping, the temperature profile is more severe and the velocity profile is more severe at the wall. So you have a lot higher H. So here we're trying to plot H as a function of location. Well, if you go back to chapter 7, we're in chapter 8 now, but in chapter 7 it was external flow. And they had this simple equation for the local Nusselt number is a constant Reynolds to the half, Prandtl to the third. And I know this is Reynolds number's function of, for this problem, that's for a plate, so it's entrance region. But at the beginning, it's as if you cut this and stretched it out. It's as if it's a plate of 2 pi d width, or 2 pi r, or pi d width. And it's like the boundary layers are growing, and they don't sense each other's presence until it starts to fill, the boundary layer starts to fill the core of the pipe. Anyway, this is a simple approximation from the previous chapter. And then you can see, oh, you can find how the local convection coefficient grows as the 1 over the square root of x in the entrance region. All right. If I have a constant surface temperature of the pipe, so here's my pipe, forget about it being, it's all fully developed when we're interested in it. They say that I have a hot, I'm plotting temperature here. If I have all of this, that's all TS, or T wall. The surface of the wall is a constant surface temperature. If I come in with the mean temperature of the fluid like this, what does the mean temperature of the fluid do as you go down the pipe? Does it go straight line? No. It's going to be a curve like that, isn't it? What does that curve look like? Your favorite curve, the hyperbolic? No, it's no hyperbolic. It's a Bessel function. No, it's no Bessel function. It's a sine wave. No, it's not a sine wave. What is it? Exponential. Exponential. So what happens is you have a larger delta T that drives the heat transfer early on, but once you've added some heat into the fluid, the mean temperature increases and the delta T decreases. You're getting closer to the surface temperature. A little more challenging mathematically than the Q double prime is constant. So this is equal to a constant, the wall temperature. All right. So That's what I just sketched. If you go back to the entrance region, regardless if it's constant temperature, you get a higher H in that entrance region. All right, I need to switch to another packet here. Just give me a minute. We've talked about the hydrodynamic considerations, velocity profile, talked about the thermal considerations, especially that mean temperature of the fluid. Now you need to do the energy balance. Energy balance. And then we can get a lot of correlations for different configuration. Look at this word, correlation, correlations, correlations. What do you think? And then we're going to skip some of these. That's nice. So we have fully developed pipe flow with constant surface heat flux. We just talked about that. Somebody has a region right in here. We just pull it out. You have the mean temperature at X, and you have the mean temperature at X plus delta X. So how did that change? It depends on the Q double prime times pi d times delta X. That's the rate at which heat is being added from the wall. And so the energy balance equation is that we have the mass flow rate times the specific heat times the exit temperature T at X plus delta X minus the mean temperature at X is equal to the rate at which it's flowing in. It's like in from the flux. You could put a perimeter here instead of pi d, whatever. I'll put pi d delta X. What do you think you do with that delta X? Divide both sides. What do you think you do with this one right here? You take the limit as delta X goes to 0, and then you get the rate of change of the mean fluid temperature, m dot c equal to q double prime pi d. So it just shows that this is going to be a constant positive slope out here. Actually, it doesn't even matter. It's in both regions, entrance as well as fully developed region. All right, harder case. You take a little section of the pipe like that at X to X plus delta X. You have the mean temperature at X. You have the mean temperature at X plus delta X. Okay. How do I have heat being transferred into it, Q coming in? It'll be an H times an area, pi d delta X, times the temperature difference, the constant surface temperature, minus the mean temperature of the fluid. Because we're going to let this shrink, let's just put the mean temperature at X right there. Mean temperature at X. So our energy balance says the mass flow rate, specific heat, T at X plus delta X minus T at X, divided by, well, I'm getting ahead of myself, is equal to H pi d delta X Ts minus Tm at X. Okay. Divide through by delta X, and you get the rate of change of the mean temperature, m dot c. Then you have H pi d Ts minus Tm. You could introduce theta. What would be theta? A logical theta would be Ts minus Tm. So if that's true, then I need to put an M right there to emphasize that. Then what is, this would be minus m dot c d theta dx is equal to H pi d theta. You see that? And so I'm going to scroll it down just a little bit. D theta dx is equal to minus, you have a bunch of terms, h pi d divided by m dot c theta. Hey, that's a nice differential equation. Ordinary, first order. I just need one initial condition, put the theta at x equal to 0 is equal to theta naught, and you can solve it, can't you? You get that exponential. The temperature difference starts at some value and then goes down to 0 after a long time. What is my analytic solution? Theta is equal to theta naught e to the minus m dot c divided by h pi d t. Oh, I messed that up. Let's put h pi d divided by m dot c t. There. Does that look okay? All right. I can see I'm not going to get to the second problem that I wanted to get to today. Yeah, we just solved that one. We just got this solution exponential. What did I do for p here? I know that's confusing, right? When you see this p in this equation, that's pi d. Why did they use p for pi perimeter instead of pressure? Sorry, recycling p. All right. All right. This one's a tough concept. It's a log mean temperature difference. What does that mean? Let me back up a little bit. Insert new page. So if I have flow in a pipe, and I come in and I go out, and I have the temperature of the surface here is constant of the wall. Just say that's constant. And I have the temperature inlet at 1 and the temperature outlet at 2. And I'm talking the mean fluid temperature at 1, the mean fluid temperature at 2. Somebody would like to have a very simple equation that says the total rate of heat transfer is the convection coefficient, the total area, times an appropriate delta T that drives it. And you're thinking, you say, well, a good estimate of that delta T would be Ts minus T1. But then somebody else says, well, another estimate would be Ts minus T2. And remember, we just worked out that profile. Maybe the surface temperature is constant and it's an exponential. And so this delta T at the exit, delta T2 versus delta T1, they're not the same at all. This one could be 50 degrees C, and this one could be 2 degrees C. So which one do you use? Well, the first good approximation, and most students will do this without knowing anything about the log mean, they'd say, I'm going to take the 50, I'm going to add the 2, and I'm going to take the average. Wouldn't that be like 26? You know, they would just say, an okay approximation would be that they would say, delta T average is equal to delta T1 plus delta T2 divided by 2. And often it'll get you in the ballpark and it's not that bad. But the better is the log mean temperature difference. What is that one? So LMTD. So the log mean temperature difference, or sometimes delta TLM, I shouldn't have put TD there, is equal to delta T1 minus delta T2 divided by the natural log of delta T1 divided by delta T2. What? This is some of the craziest stuff. But this works. And I know I'm running out of time. I still got 10 minutes. But you should play with this equation before we get into the derivation of this equation. Let's do this. For this problem, we just worked out what this approximation, just doing a, what do they call that? It's just a regular averaging. But this is a logarithmic averaging. the log mean temperature difference. Okay, so if we had 50 and 2, isn't that 52 divided by 2? Isn't that 26? Somebody run this one right here. So what we'll have is 50 minus 2 divided by the natural log of 50 divided by 2. What do you get? 14.9. 14.9. A lot difference, isn't it? Right? Did anybody else verify that? Who has a calculator? Let's get a couple more to verify it. You got it? You agree? A couple more. You agree? Okay, let's do this one. That's a big difference between 26 and 14.9. Let's do this one. Let's say delta T1 is 50 degrees C, and delta T2 is 30 degrees C. The one would say the delta T average is 40 degrees C, but what's the log mean temperature difference for this one? Delta TLM. Can you run that one? 39.1 degrees C. You're fast. How do you do that so fast? Sean, how do you do this so fast? You're anticipating my numbers, or are you just fast? Somebody verify that. A couple verifies. See that the difference isn't that bad, but as the second delta T gets further away, like 50 and 2, that's pretty extreme. You're really seeing that exponential shape kick in, and you want to use the log mean temperature difference. The log mean temperature difference will always give you the correct approach or the correct answer, where this regular averaging, I'm trying to think of it, algebraic averaging, or is close when you have cases like this. All right, you want to see the derivation? There it is. It's in the textbook as well. How are you feeling? Pretty tired?
Very tired, yeah.
Very tired. So what we're going to do is we're going to stop here. If you have some questions about the exam, I'll be up in my office. This is really a good chapter, so please spend some time in it. It's very applicable. If you get out and do anything in mechanical engineering heat transfer, you're going to encounter pipes and internal flow. Thank you.